Today's presentation, we will be going over Unified Modeling Language, also known as UML, Test-Driven Development, also known as TDD, and Software Security, or Cybersecurity. We're going to touch on what exactly UML is, we're going to touch on what exactly TDD is, and what software security is. And then in the end, I'm going to summarize everything that we went over in this presentation. So, what is UML? Well, within this context, we're going to cover its origin, its history, overview, its example, an example on it, and my thoughts on UML. So, it was released in 1994 by 3 object-oriented analysis experts. The goal was to create a new object-oriented model that would combine all the best features of their object-oriented analysis and their design methods. The result from above was a brilliant combination of the Booth method, the object modeling technique OMT, and object-oriented software engineering OOSE. UML has also been influenced by other object-oriented notations such as Meller and Schleyer, Code and Jordan, Wurfs-Brock, and Martin and Odell. By 1997, UML became a de facto industry standard for object-oriented software development and is still widely used today. In its history, in 1997, UML was adopted as a standard by the Object Management Group, OMG. Rational Software, which was the company that employed the 3 creators of UML, it had established a UML Partners Consortium in which many companies contributed to the UML specification. One of the big ones was HP. Shortly after UML 1.0 was released, the UML Partners Consortium was joined by a few more companies that contributed to the production of the revised UML 1.1. One of those notable companies was IBM. UML 2.0 major revision was replaced version 1.5 in 2005, and the most current version of UML is 2.5, which was released in 2013. There are 2 categories of diagrams in the UML 2.xx specification: structure diagrams and behavior diagrams. Structure diagrams consist of a class, component, deployment, object, package, composite structure, and profile diagram. Behavior diagrams consist of a use case, activity, state machine, sequence, communication, interaction, and a timing diagram. There are several diagrams because different people need different diagrams to represent the software for their purposes. I was actually surprised to see at the many different roles that are included in the software development process and the different angles that are needed to be used to look at software for them to complete their job, hence all the different diagrams. So yeah, I have mainly only used class diagrams, and so when I found out there was all these other ones, I was very surprised. As I've mentioned, of the above diagrams, I have used the class diagram the most. It's actually the only one I've used. The next slide contains an image of a class diagram example. So here we can see that it says it's a class diagram for order processing. So at the top left here, we got the client. And then at the top section of this box, this class, this is the client class, we have the instance variables. And then here at the bottom, we have the methods. Here it shows relationships among classes and associations. And then here we have the order class. It has instance variables, and it also has 2 methods. Here's the stock class, has instance variables and a few methods as well, and so does the product class. My thoughts on UML. I like UML because it enables me to write code at a more constant speed, as I have the classes mapped out, and generally I find this leads to a better experience in the entire development process. I've developed or written code without using UML, and I've done it after using UML, and I gotta say, using UML definitely, I don't know if it saves time in the end because you spend time writing the UML instead of the code, but it definitely saves time on writing code. I don't spend near the amount of total time writing code as when I do without writing UML. I always find myself stumbling when it comes to remembering how to express relationships and inheritance in a class diagram, but everything else I seem to remember no issues. I once had to create a bank application in Java, and I made a UML diagram before writing it. That proved to be a great idea, as there were too many classes and details for me to remember in my head to just start writing the code immediately. That's exactly where you end up writing error-prone software, and it really reduces the quality of the end product. I would recommend using UML on harder projects, as it may be overkill for unnecessary for a small project with few classes. Maybe use it on smaller projects while you're still trying to learn it. A great resource to learn about UML is tutorialspoint.com/UML. I've also looked at plenty of other tutorials on that website too, and it's came in handy plenty of times. So it's got more than just UML on there. There's also programming languages, and more than just the class diagram on UML is on there too. So in this section, we're going to cover test-driven development. We're going to go over its origin, its history, overview, example, and my thoughts on TDD. Concepts of test-driven development are related to the test-first programming concepts of extreme programming, which first date back to the early 90s. Before I go on with the rest of the slide, I do want to say that in my research on the origin of test-driven development, I found a lot of conflicting sources. I found some sources that pointed me toward literature that dated back to the 1960s, and I also found many sources, actually many more sources, that led me to Kent Beck and the extreme programming of the 1990s. With that being said, I believe that it more closely goes back to Kent Beck, but test-driven development wasn't necessarily made before Kent Beck, but ideas related to it were stirring around before the 90s. So I'll cover that in the slide, but I just wanted to say that before reading it off. Okay, Kent Beck is the programmer credited for establishing its wide use. There were other test-driven development-like approaches before Kent Beck, but he is the one that made a more mature concept out of it. There's a link below that has an interview with Kent Beck and why he believes he only rediscovered test-driven development, not invented it. And that actually, without you having to go into the interview, I can just tell you that it's basically because of what I said. There were, immature concepts of test-driven development or ideas in its infancy. So it really wasn't matured until Kent Beck came around. JUnit was actually a port of SUnit written by Kent Beck, and the Java community that practice agile or extreme programming methodologies are what really helped test-driven development start to take off. That's when it really became of widespread use. Alright, so let's go into the history a little bit about test-driven development. And just like with trying to figure out the origins of it, finding the history on it, I was coming across a lot of conflicting sources. So anyway, here it is. Somewhere in the early 1960s, programmers for the Mercury space program used some type of variation of test-driven development while programming punched cards. Crazy, right? In 1989, Gary Weinberg writes tests first on punch cards, and Kent Beck reads about punching the output tape. In 1994, Kent Beck wrote the first version of S-Unit and later in an interview stated that he recalled some of the reading of punching the output tape when he wrote S-Unit. So clearly reading that, had profound effects on him and may have well actually led to the development of TDD as we know it today. It just goes to show how important reading is, right, kids? In 1995, Kent Beck demos TDD for Ward Cunningham at a convention center. JUnit launched its first version in 2000, and the Eclipse IDE released support for JUnit in 2002, and Kent Beck released a book named Test-Driven Development by Example. I actually think I might want to check out that book. Reading about test-driven development from the creator, the one credited for it, seems like it could be a great opportunity to learn. And then I posted a link of a timeline that shows the evolution of test-driven development, and that was actually very useful in my research. So if you're interested, go check it out. Alright, so let's go over a slight overview of what we've covered here in TDD. The foundation of TDD is automation testing, in which there are 3 types, all listed below. Unit testing, which we covered a little bit in class with JUnit, and that is the testing of individual units of code. Integration testing, which is the testing of multiple individual units of code as a system to see if they still pass tests when all combined. This is especially important before releasing any code into production. Performance testing, also important to do before production, as you don't want the clients or consumers of your services to have any negative experiences. Anyway, performance testing is the testing of how speedy your code executes, usually used in conjunction with an increased load to simulate real-world scenarios. So, like if it's a website, they might try to increase the traffic to simulate what real traffic may be, because if you were testing it this entire time, I doubt you had real traffic flowing to it. You were probably just the one looking at it while you were testing it, or maybe you and a few other developers / testers. In either case, it doesn't amount to the amount of consumers that will be on your, or customers that will be on your service. Test-driven development is a process in which a programmer writes test cases that fail first, and then writes test cases that pass, and finally refactor their code. It's an iterative style, or iterative process. So you're gonna first write tests that fail. You're gonna make sure they fail, and once you got that, that's good. And then you need to write test cases that pass, so that way you have failed ones and passed ones. And then when you first write them, they don't need to be neat. It always helps to be neat, but they don't need to be perfect. The main idea for writing these first tests, or your first pass through these first tests, is to just write something that works. Make sure that it fails the test when it should, and it passes the test when it should. That is the biggest priority. And then you can refactor your code. Make it neat. Change the names of variables that don't have a name that makes sense for what they're doing. Just little things to refactor your code and make it neat and make it easier to read and more maintainable. Using the test-driven development approach can produce higher quality software as more testing is done, and it's done throughout the entire software development lifecycle. Typically, if you're not taking a test-driven development approach, you're going to do some requirements gathering, you're going to write some code, maybe do some UML, then write some code, and then you're going to test it. And, things are going to fail, you're going to write some more code, and then you're going to retest, and that's going to be another iterative cycle until all tests finally pass. Testing software and preventing bugs from reaching production is much cheaper than fixing bugs that have made their way into production. And that that's cited everywhere that you read about software testing, or if you know anything about software testing or the costs of software, and you'll know that's true. Fixing bugs after they've reached production is very costly. You have no way of telling how that bug is going to affect the client and how much damage it's really going to cause. So best to just eliminate them before they reach production. Test-driven development provides an increased sense of confidence as all software has been tested. Test-driven development requires all parts of the test, or I'm sorry, all parts of the software to be tested, not just parts of it. So you can ensure that using TDD that everything is going to be covered and tested, which ends up in a higher quality end product. TDD also produces easily refactorable code by nature because it requires the total test coverage. So, killing two birds with one stone. I like it. Here's an example of test-driven development versus a traditional cycle of development. And it's pretty straightforward. As I've mentioned before, the test-driven development is an iterative process. So, you're gonna write some code, run the test. If it fails, you're gonna, rewrite the code and rerun the test. If it passes, then you're gonna refactor the code. Then finally, once you've done this for whatever function you're working on, you're gonna move on to the next function, and the whole process repeats. You're gonna write the code, run the test. If the test passes, good, move on to the next function. Or I'm sorry, refactor, and then move on to the next function. If the test fails, you're going to rewrite the code and test again. Whereas a traditional cycle, you're going to get all of your requirements, figure out everything that's needed. You're going to write all of your automated tests. You're going to run the tests, and then you're going to fix the errors. And that comes at the end of the development cycle, well, writing all the automated tests and then running those tests. Obviously, you have to do requirements gathering before writing code. But yeah, in a nutshell, that's how they are. All right, moving on. So here are my thoughts on test-driven development. I personally haven't used it often, and as a matter of fact, I learned about it in this class. I had heard about it, but that's really the extent of it. I had no idea what it was. I never looked into it. I just didn't know anything about it. When we did the JUnit assignment, don't remember what assignment that was, or what number assignment that was, but I did get a good feel for it, and I did kind of like it. It was a little weird to learn about at first, but it all kind of felt a little more natural after spending some time writing the code for it. And after I executed it and kind of seeing how it worked, that's when it really started to grow on me. The test-driven development assignment showed me that it was easier to think of use cases and possible fails before writing code, and then to write code that forced those fails so they could be handled correctly, as opposed to have a fatal crash at runtime. And that's never a good thing. You definitely don't want that to happen. It's different if it's a personal project, big whoop, just, fix the code and rerun it again. Hopefully you didn't lose much progress. But, for something that's out in production or something that's customer facing, you never want to have any fatal crashes. Definitely provides a poor experience, and, that could equate to many things. That could equate to lost customers, which equates to lost profit. So, you don't want to go down that road. Prevent fatal crashes. Use test-driven development. It's been proven to work. Not to completely eliminate bugs, but definitely helps eliminate most. Much like UML, I would recommend using it to ease the process of development, to decrease the time needed, and produce a higher quality end product. So, yeah, if you want a higher quality end product and you want software that's less error prone and you don't want to be stuck fixing a bunch of bugs at the very end of writing all your code and then having to rewrite all the code and retesting, then just do this from the beginning. Save yourself some time, save yourself the hassle. I know it sucks, but just do it. So, what is software security? Well, software security is a big subject, a very, very big subject. We're going to go over, just like the other two subjects, its origin, history, overview, example, and my thoughts on it. Alright. The origin of cybersecurity dates back to 1971 with a man named Bob Thomas, not to be confused with Dave Thomas, the founder of Wendy's. Anyway, he apparently created the first ever computer worm that would bounce between computers on a network and printed, "I'm the creeper, catch me if you can." Can you guess the name of the software? It was Creeper. Later, the man who invented email, Ray Tomlinson, tinkered with the program and made it self-replicating, and he named it Reaper. He must have found this program, thrilling to work with, somehow, some type of exciting. In 1986, a German hacker, Marcus Hess, hacked into a gateway in Berkeley and piggybacked onto the ARPANET, which was kind of like the first internet. After which he got access to over 400 military computers in an attempt to sell the KGB classified information. It was really at that point in history that cybersecurity was actually seen as a threat. Viruses and things before that point in history, they were known to be a threat, but many people weren't writing them, and they weren't really a threat because personal home computers weren't really a big thing yet, so there really wasn't a need for much computer security, or nowhere the same amount that there is now. There's computers in everybody's home, multiple, in fact, just about everybody's home. Alright, in 1988, Robert Morris wanted to gauge the size of the internet. So, he wrote a program to propagate across many networks, infiltrate Unix terminals, and duplicate itself. The program was so aggressive that it brought the early internet to a slow crawl, effectively the first denial of service attack. This led to the formation of Computer Emergency Response Team, now is known as the US CERT. In 1989, the AIDS Trojan, which was the first ever ransomware attack, was distributed through floppy disks. That's crazy. Like, how did that work? Did they just, go and stick a bunch of floppy disks in everybody's computers, or they distribute them and tell people that they were some other type of software they weren't? I did not research the AIDS Trojan that much, so I couldn't tell you, but now I'm really wishing I would have. Anyway, in 1990, the Computer Misuse Act was established in the UK and made illegal the unauthorized attempt into a computer. Thank God for that. There is way too much data and privacy issues nowadays with all the information that we store on our computers. And sometimes it's not even stuff that we're trying to store on there, it's like cookies, you accept it when you join a website or visit a website, there's some kind of little pop-up that says they use cookies, and you accept it to get rid of it just because you quickly want to, view the website, but, you don't really know the effects of that. What that is that website storing data about you, and, that's one of the many ways that you see personalized ads on different websites or different apps, and it's just crazy to think that it's just so easy to give away your information. So beware of what you do. Think about those cookies you accept. I mean, it may seem not so harmful, but what if that company then sells that information to a bunch of other third-party companies, and then effectively your information's everywhere, and then you have telemarketers, and you have spam in your email, and phishing, which is voice phishing, attacks being attempted on you, all because you accepted cookies. It's really crazy. Anyway, um, thank God this issue was noticed to be huge eventually, because in 2002, George W. Bush created the Department of Homeland Security, which eventually established a division solely for cybersecurity. So that's how big of a deal cybersecurity really is, people. Cybersecurity is especially important in our time because as technology becomes more advanced, so too does the malicious software. There are so many different types of attacks that to go over all of them in this presentation would be way too cumbersome and, honestly would be kind of out of the scope. Example malicious software, also known as malware, include ransomware, computer viruses, cryptojacking, or crypto mining, which is basically infiltrating a remote computer and using it to mine cryptocurrency, such as Bitcoin, spyware, adware, worms, and many more. Some example attacks include SQL injection, also known as SQLI, XSS, or cross-site scripting, denial of service, distributed denial of service, phishing, and vishing. The Equifax breach in 2017 left the company with $4 billion total in debt and damages, and they're still paying that off. That was 3 years ago, almost 4 years. $4 billion is a lot of money. Just goes to show, how expensive cybersecurity is and how well it could pay off if, just take some preventative measures. I didn't research that too much, so I don't know if, I'm sure they did have some preventative measures in place, but clearly not enough. Anyway, the worldwide spending on cybersecurity is projected to reach $133.7 billion in 2022. That is nuts. Anyway, GitHub is a platform for software developers. It's kind of where they submit their code and other developers can download it and work on it, and it's a version control system. Anyway, the amount of traffic when they got attacked in February 2018 from a distributed denial of service attack was 1.3 terabits, which equals 168.75 gigabytes per second in traffic. That is crazy. I think they said it lasted for a few days as well. So, during that time, I can imagine that everybody that was a member of GitHub had no access to their code repositories. So I'm sure that was a headache for a few companies and for people working on personal projects, especially if they had no local copy of it on their hard drive. My thoughts on software security. It's no topic to be taken lightly. It should be thought of during all stages of the development process, and there are tons of stats online of the costs and the repercussions of cybersecurity. I implore you to go and read about it. Cybersecurity is only going to become more advanced and costly as time progresses, as does all technology. Even for public sources that, there's no authentication needed or authorization needed to access, preventative security measures should still be taken to ensure the resources maintain their availability or are available at all times. Maybe even some integrity measures should be taken too to make sure that these free resources aren't messed with and then misguiding the public, sending out falsified information in essence. Here's a summary with my experience and thoughts on the. I have used UML class diagrams enough to say that I'm pretty educated on the subject, but not enough to say I've mastered them. I haven't really used any of the other diagrams, and there was a bunch of them as I mentioned earlier. So I don't really know how effective they are, but I can imagine that if there's a place for them, there's a time. UML was easy for me to pick up and easy to read when it comes time to write the code for the project. I've only ever used test-driven development in this class before, but now that I've read about it, I'm surely going to practice it more. I might even start with that Kent Beck read that I mentioned earlier, his only book. Since he's the creator of TDD, why not read about it through his book? It's a simple concept with profound effects. And I've taken a cybersecurity course, and my final was on SQL injection attacks. I learned a great deal there, and as a software tester with my current employer. In my current position, I have identified XSS vulnerabilities within our web application, and hotfixes were applied to fix the issue. I personally like to use UML class diagrams before writing any code when I have a project that requires many classes. It allows me to see the big picture and put it on paper and then code, as opposed to having cycles of envisioning the big picture and writing code, which is typically more error prone. I enjoyed learning about TDD and am now curious about BDD, which is behavioral driven development. I plan on researching it more and likely practicing it as well. I enjoyed the confidence of writing quality software that was a direct result of TDD. I always enjoy learning and practicing cybersecurity, from malicious attacks to just simple infiltration. I plan on learning more about cybersecurity and ways to prevent malicious attacks. I hope this presentation has been informative for you. With that being said, have a good one.